Hi everyone, this is our group. We use transformers to train on JSP chorus dataset to generate symbolic music. We work on two symbolic music generation tasks. The first task is on condition generation, where the model learns the distribution of chorus and generates a new SATB piece from scratch. The goal is to learn the overall distribution of Bach-style chorus, then sample a new four-voice chorus from the model. The second task is condition generation, where the soprano melody is given and the model generates the alto, tenor, and bass harmony. For evaluation, we look at inactive thought likelihood and perplexity, but we also include musical properties such as pitch range, validity, and note density, because low lows can not always mean the generated music sounds musically correct. We use JSB chorus, which is a 382 4-pad harmonizations by J.S. Bach, taken from the C-drum JSB chorus dataset repository in its 16th note quintiles voice-separated format. Each choral is represented as a sequence of time steps, where every time steps is a four-tuple of MIDI pitch numbers for soprano, alto, tenor, and bass, with -1 indicating silence. This is the pre-processing code. Here we import our dataset, and this is an example from our dataset. We did some EDA for the dataset, which are pinch distribution, sequence length distribution, note density, and repeated chord transitions. The EDA results show that the JSB chorus dataset is clean and structured. The pinch distribution shows that the four voices occupy reasonable and different pinch ranges. Bass stays the lower range, soprano stays in the higher range, and the alto, tenor are in the middle. The length distribution shows that most chorals have moderate sequence lengths, while a few are much longer. This means padding is needed during batching. The node density plot shows that most time steps contain all four active voices, so the data is not very sparse. The repeated chord transition ratio is around 0.637, meaning many neighboring time steps contain the same chord. This is expected because the data uses 16th node resolution, but it also means the model may learn to copy the previous chord frequently and affect its performance. Overall, the dataset is suitable for symbolic sequence modeling.
Okay, let's dive into test one. So in this test, we use transformer model to generate music and choose unigram, bigram, and LSTM as our baseline. Unigram is very simple and fast, but it doesn't use any sequence context. Bigram is efficient and easy to implement, but cannot model long-range dependencies. LSTM is more flexible but slow to train and struggle with very long-range structure. Transformer can capture longer range dependencies, but it is complex to be implemented. The input is a previous chord tokens, and the output is the next chord token. After generation, we decode the chord sequence back into four voices and save it as a MIDI file. The training objective is negative log likelihood, so the model learns to assign higher probability to chord sequences that looks like real chorals. So in our notebook, the transformer uses 256 dimensional embeddings for attention heads and 4 layers. We also use position encoding so the model knows the order of the chords. Since this is a generation task, we apply a causal mask so the model can only look at previous chords and not the future ones. A key design choice here is a joint for voice chord tokenization. Instead of predicting four voices separately, we'll combine them at each time step into one SATB chord token. This makes the pipeline simpler and it allows the model to learn vertical harmony directly. And this is the implementation of our pipeline. And this is the implementation of our baseline models, which is unigram, bigram, and LSTM.
For model evaluation, we compare test negative log likelihood and perplexity across different models. Lower perplexity means the model gives higher probability to the correct next chord. This is the implementation of machine learning objectives evaluation. The transformer gets the best result with a test MLL of 3.78 and a PPL of 43.96. This is much better than the LSTM baseline. The bigram and unigram baselines are even worse because they only capture simple frequency or local transition patterns. Not only MLL and PPL, we also check the generated sample directly because a model can have good likelihood but still generate boring or repetitive music. This is the implementation of generating samples from different models. Music properties including pitch range validity, note density, repeated chord ratio, mean length, and in-range rates. Here we compare 20 generated samples from each model. The transformer has the best overall musical structure. Its pitch range validity is 98.5% and the note density is exactly 4, meaning it usually keeps all four voices active. It means length is close to the real chorus. However, the main issue is the repeat chord ratio. In the training data, this ratio is about 0.63, but for the transformer, it becomes 0.84. This means the transformer learns to hold chords for a long time. That helps reduce loss, but it can make the output sound too static. The LSTM is less repetitive with a repeat ratio of 0.52, but its pitch range validity and note density are worse. The bigram and unigram baselines look valid in pitch range, but their repeat ratio is almost zero, so they do not capture realistic temporal structure. So the main takeaway is that the transformer is much better at modeling chord sequences. Its self-attention can capture longer musical content, while the baselines mostly rely on short-term or simple statistics. But MLL and PPL are not enough. We also need diversity, repetition, length, and musical validity checks to understand sample quality. For task 2, we do condition symbolic generation. Here, the model is not generating music from scratch. Instead, we give it the soprano melody as input, and the goal is to generate the other three voices, alto, tenor, and bass. So this task is basically homorization. The model learns how to add harmony under a given melody using the style of JSB chorus. For each time step, the input is the soprano pitch and the output is the predicted ATB notes. After generation, we combine the soprano with the generated harmony and export the 4/4 voice result as a MIDI file. In task 2, we construct condition transformer as our model and only use LSTM as baseline. LSTM is more flexible but slow to train and struggle with very long-ranged structure. Transformer can capture longer range dependencies but complex to implement. This is our implementation of condition transformer for task 2. The input is only soprano melody. We pass the soprano pitch sequence into a bidirectional transformer encoder, so the model can use both earlier and later melody context when predicting harmony. The output has three separate heads, one for alto, one for tenor, and one for bass. Each head predicts the pitch for its own voice at every time step. The loss is the sum of the cross entropy losses for these three voices. The key design choice is factorized per voice prediction. Instead of treating the whole alto-tenor bass combination as one huge token, we predict the three voices separately. This keeps the vocabulary smaller and makes training easier. One limitation is that the three voices are predicted independently, so the model may still make some voice leading mistakes. That is why we later add musical checks like voice crossing and pitch range validity. This is the implementation of baseline model bidirectional LSTM.
For test 2 model evaluation, we use negative log likelihood, perplexity, and time step or frame accuracy to evaluate how well the model generates harmony from the input soprano melody. On the left, the training curve shows that the validation negative log likelihood drops quickly and then becomes stable after around 30 to 50 epochs. The frame accuracy also improves and stays around 36%, so the model is learning a consistent mapping from soprano to the other voices. And this is the implementation of the evaluation for both transformer and bidirectional LSTM. And this is the score for the test set, where the transformer gets a test negative log likelihood of 1.91, a perplexity of 6.81, and frame accuracy of 35.7%, while the bidirectional LSTM is slightly better than transformer with negative log likelihood of 1.82, perplexity of 6.19, and frame accuracy of 41.5%. So for this task, the bidirectional LSTM baseline actually performs a little better on likelihood and accuracy. Other than negative log likelihood, perplexity, and frame accuracy, we also check musical rule metrics for both models. Music properties including pitch range, validity, note density, repeated chord ratio, voice crossing ratio, and length. This is the implementation of music properties evaluations. And here we compare 20 generated samples from each model. In this table, we compare their score on the evaluation for the music properties. So both models actually have very high pitch range validity of 0.99 and same note density of 3.995 and length of 242.6. Transformer has 2 times more voice crossing and 3 times lesser repeated chord ratio compared to bidirectional LSTM, meaning that it changed harmony less often than the baseline and having more variation in harmony chord. So the main takeaway from this table is that the bidirectional LSTM is stronger on prediction accuracy than transformer, while the transformer still produces valid harmonies and also it has fewer voice crossing issues.
For related work, we look at several previous approaches to JSBach, chorales, dataset, and symbolic music generation. Earlier work like Allen and Williams in 2005 used probabilistic methods for chorale harmonization. Later in 2012, Boulanger Lewandowski used JSB chorales as a benchmark for polyphonic music modeling. So this dataset became a common test case for symbolic music generation. Deep Bach is closely related to our text too because it also generates Bach style chorales and models different voices. Coconut is also relevant because it uses bidirectional context and can fill in missing parts of music, which is similar to harmonization. Music transformer is important because it shows that attention-based models can capture longer musical structure. Compared with these works, our project is smaller and simpler, but follows the same generate direction. For text 1, we use a transformer to model full chord sequences. For text 2, we use soprano melody as the condition and generate the other voices. One thing we learned is that standard metrics like accuracy or perplexity are useful, but they do not fully describe musical quality. So we also include checks for music properties like pitch range, repetition, and voice crossing.
We are going to play 3 generated samples for task 1. And now we are going to play 3 generated samples for task 2. And we think that the music generated in task 2 is much better than in task 1.
Thank you.